So I'm very happy to be here talking about this on the 60th birthday of Maria Carmen. This is rather loud, isn't it? It's reverberating. Yesterday, talking to Cidinha, I realized that I'm probably here in this workshop, the person who has known Carmen longer. I first met Carmen when I went to Warwick to do my PhD. Carmen had just left to Southampton. But she liked the place and she kept coming back for visits. So that's how I met her. And then I borrowed her singularity theory notes to make my course. And we've been friends ever since, and we've been in contact ever since. That's a picture from that time. That's the only picture of Carmen I have of that time. If you think she's looking strange there, look at the rest of the group. I'm here. I'm the clown. Okay, so we had a good time at work. That's why she kept coming back. Later on, we went our ways to different countries. And the next time I met Carmen was when first time I came to São Carlos, and she was in Viçosa. So she invited me to Viçosa. And it was great meeting Carmen again, and with all her energy and getting Viçosa going and getting everything going well. It was really fantastic. But after a whole morning of talking, we talked and talked and talked, and then I realized that we were talking in Portuguese. we used to speak in Spanish. So, Carmen, thank you for all these years. It's been a pleasure. Let's go on. Okay, this talk, there's not much in singularities in this talk. It's more dynamical systems, because in the meantime, I diverged away from singularities. I'm going to talk about a general problem a particular case of a general problem that I'm interested in, is how to generate models for bursts, like this sort of shaped response. This is time, and this is a response from a nerve cell, supposed to be. And how to get this sort of bursts by in coupling ordinary differential equations with two time scales. What I would like to do would be to do a general theory of this stuff. I started doing just one example, coupling two Fitzhugh-Nagumo equations to get the feeling of how I could deal with the general case. So far I haven't got to the general case, so I hope some later time I'll do that. It's work in progress. It's also very slow progress because it's collaboration with myself, and I'm very bad at collaborating with myself. I'm better when I'm working with others. So, okay, the problem is getting models for bursts. And the mathematical method is to look at models with two time scales. So you have two differential equations, one of which, let's see if I can point with this thing without getting it messed. Okay, one of which is much faster than the other. So evolves faster with time than the other, I mean in any dimension. And the idea is that in a model like that, you can study the two time scales separately, and it's called the singular limit. So one of the time scales is to look at things in a slow time, so the slow equation stops. You almost don't see it moving, and the fast equation goes slower and you can observe it. So you rescale time in this way, here. And something fishy here. Okay. And is there something wrong with the microphone? Maybe it's, okay, it's tangled in my hair. I see. So the fast equation dominates, and the slow equation stops, right? You rescale time, your epsilon, which is telling you the speed goes here. When epsilon goes to 0, this is y dot is 0. So the slow equation, the slow variable stops, and you only see the fast time. Then you analyze that, and then you can analyze the model in the fast time separately. So you imagine everything, the fast equation, the slow equation dominates, and the fast equation has gone to an equilibrium position. So you have this slow manifold, which is defined by the slow equation being 0, and you have the fast equation being 0, and the slow equation dominates, and you analyze it separately. So you have two lower dimensional models that you can analyze separately, and that's easier, supposedly, than analyzing the whole thing. An example is the Fitzhugh-Nagumo equation. So it's two-dimensional, x is in R, y is in R. Well, there are several things called Fitzhugh-Nagumo equations. There are slight variants of this. I'm choosing one. I think I'm choosing Nagumo's equation, but that's a partial differential equation, and I'm doing it in an ordinary way. But anyway, the fast equation, that's wrong button. The fast equation is a cubic. The slow equation is linear, so it's very simple. And in the fast dynamics, you have this cubic equation, and the equilibrium points lie in the slow manifold, which is phi of x equals y, which is where x dot is 0. Well, dot is derivative with respect to time. So you look at the part of this slow manifold, here it is. This is the slow manifold. And you look at the part of it that it attracts the fast flow. Here is the fast flow going into the slow manifold. Of course, here it goes away from this bit of the slow manifold. And of course, there are parts of the slow manifold which attract the fast flow. And there are parts that repel it or don't attract it anyway. So the boundary of stability here is the set of folds of the slow manifold with respect to the projection into the slow variable. Okay? And this one. So you analyze the dynamics of the slow manifold. Here I've drawn the place where the slow manifold, the slow equation is 0. When you're on the slow manifold, you're sort of on this part. Y dot is negative, so we go down. Okay? Here, y dot is 0, so it's an equilibrium point for the whole equation. But if you start below here, you follow it up to the equilibrium. But if you start below this fold point, you zoom here, then follow the slow manifold, then you run out of slow manifold to go to, and your flow is still going up, so you zoom here, and then you go down back to the equilibrium. So instead of going smoothly to the equilibrium, you have this long transient that takes place that goes round before you return to the equilibrium. That's for when delta is 0 or close to 0 is similar. If delta is smaller, is negative and sort of a large negative, then this line moves down, right? And when it's down here, then you get a different story altogether, because you don't have an equilibrium of the equation here anymore, which doesn't, so you don't have this equilibrium that attracts the flow. And so if you start around here, you go fast here, go up slowly, fast here, slowly down, and then you return into this area above the point where you started. And if you start somewhere around here, you return below the point where you started. So somewhere between points starting here and starting here, if you start on top, you return lower down. If you start in the bottom, you return up, further up. So in the middle, you should return to the same point. So you should have a closed curve here, somewhere, right? And this curve corresponds to a solution of the equation which has, if you draw it in time, see if you can see, if you put time here, then it's going to do something like go, and you're putting like x here, you go very fast to a value, and slowly down, and, well, very fast here, and slowly up. And then you repeat. So you have this sort of square wave shape, which is called a relaxation oscillation. Okay? So what I'm going to do is couple two of these to see what happens. So I just put index 1 and index 2 in the variables of the equation, copied twice the equation, and then added the coupling term here, which pushes the equation back I'm doing this K2 coupling constant and a K1 coupling constant positive, so I'm trying to reduce the difference. Okay, minus K2 reduces the difference. And I'm trying to force the equations to operate in the same way and see what happens. So you have a two-dimensional fast equation, right? It's two fast variables, x1 and x2, and a two-dimensional slow manifold, which is with the slow variables y1 and y2. So I've written it in less space, the same equation. The first thing you get, since I've coupled the equations, trying to, this thing gets on my hair. Since I've coupled the two equations in a way that pushes them tends to reduce the difference, if the coupling constants are very large, actually you can estimate how large in terms of the other parameters in the equation. If the sum of the two coupling constants is large enough, then the diagonal is attracting. The diagonal is x1 equals x2 and y1 equals y2. So if you have a very strong coupling constant, what happens is that two equations behave like one equation. Two copies of the same equation behaving in exactly the same way, right? In general, this diagonal is always flow invariant, but usually it's not attracting. If this K1 plus, well, if K1 plus K2 is 0, it's not attracting, right? The two equations behave independently. But, so I'm interested in looking at the dynamics when the coupling strength is small, but positive, of course. When it's 0, it's easy. Okay, so let's see what is going to be the scheme. I'm going to have a geometric part, which is more interesting for people here, which is looking at the equation as a hybrid system in the singular limit. I'm going to look at the fast equation, look at the slow manifold and its singularities. So it's an exercise in what our elementary singularity theory, what we learned in our first class in singularities. Then I look at the constrained equation, slow equation, on the attracting part of the slow manifold. So I have to decide which part of the slow manifold is attracting. And then look at folds and higher singularities of the slow manifold, where I'm going to get jumps, which are going to generate the interesting dynamics. It's more complicated than the first example I gave you for two reasons. First, I have a two-dimensional fast equation, so the equilibrium may change stability not only in folds but in Hopf bifurcations. So there may be parts of the slow manifold where your it stops being attracting without being folded, right? And the other complication may be that the slow equation may have equilibria on the fold line. And this happens generically in one-parameter families, of course. So if you have an equilibrium, you sort of move it with a parameter into the fold line. Of course, that's a complication, but that's what's going to generate the interest in dynamics, so that's what I'm looking for. Okay. So the first lemma is very trivial. It's the only result I'm going to prove. A slow manifold of these equations is the graph. Very simple. You look at the fast equation, the slow manifold is just setting these two things equal 0, and it's obvious that it's a graph. So y is a graph, y is a function of f of x1 and x2. The problem is, so I want to look at it projected into y1 and y2 plane, and then I may have singularities, which of course generically are folds, and there could be cusp points, and there are going to be some cusp points. And there could be more degenerate things. It wouldn't be generic, but it's a specific system. It's not compulsory to be generic, right? So that's an example of choosing a set of parameters, but it's a typical example for this equation. Okay, I've chosen these parameters for the equation. This is a projection of the folds, the line of folds, into the fast plane, the fast variables, right? I've colored the components so you can see where they go when it's projected into the slow variables. That's the fast variables. So this, let's see, I think I need my wiggly pointer. This bit here goes here. And this part here folds that way. And this bit here goes here symmetrically, right? These two components fold also like that with cusps. And then this central closed bit folds. It's a very, very, very typical. It has all the pictures we're used to seeing, right? Okay, so we have 4 cusp points, and that's it. I'm interested, well, the way you show that there are 4 cusp points is, I've done the sort of a geometrical version of or graphic version of what you do. You look at the possibly fold points, which may be more degenerate. So you write a condition here for fold points. Then you write the conditions, the second order condition to have a cusp. It's this red line. When the red line meets the blue line, you have a cusp point. This is projected into the fast variables. You can do the same thing projected into the slow variables. So, okay, you do this calculating. The proofs are boring, long calculations. So, and you get the 4 cusps. Now we're interested in deciding which components of this thing, right? This divides the plane into 1, 2, 3, 4, 5, 6 components. Which ones are going to be stable, attracting for the fast flow? And whether there are other changes in attractivity that are not folds. So we're looking at the attracting component of the slow manifold. The first result is how do you do that? You linearize the equation around the equilibrium and look for the eigenvalues, right? And you want them negative, or with negative real parts. Oops. So the first result is, in this example, there are never purely imaginary eigenvalues, which is good news because it means that the only way you can stop being attractive is at a fold or cusp, of course. So the consequence is that the boundary of stability for the equilibrium is always contained in the fold locus. And then the next result, well, then, but which part of the, which regions of that decomposition of the fast plane is attracting? The first result is that there are two intervals. Basically, the result is this. Let me draw it. I think if we cannot draw it, we don't understand it, right? Basically, is that in x1, x2 plane, all these things are not attracting. Okay? So I can find, first thing I do, I can find an interval in one coordinate and an interval in the other coordinate. If one of the coordinates is in one of these intervals, it's not attracting. Then, it's a dancing interval. At least, okay. The lines, these lines that form the boundary of this part that is not attracting are the asymptotes to the fold locus of the x1, x2 plane, right? But then I can get more explicitly exactly what is the boundary of the attracting region. Okay, so it's exactly if the determinant of of course, this is obvious. If the determinant of the fast equation is positive, then that's not the determinant of the fast equation. It's of the equation that defines the slow manifold is positive, then it's not stable. So I know exactly what it is, right? I have these fold lines here, and it's outside these four fold lines, I have an attracting component. So I'm going to forget what's in here. If you're interested in, I have saddles here, and I have unstable nodes here. So let's see how it folds up. Those are the four attracting components of the slow manifold on the xy, the fast variable plane. The blue and the red components fold like that into the slow variable plane. And the yellow and green, had to have a yellow and green, right? So yellow and green fold like that. This, you know, if you're following, then the slow fold is going to go around here and jump, eventually, at some points, jump off the fold lines, okay? And then there's a lot of superposition here. So they jump and they may fall into another component, attracting component. So let's see. So this is the same slide I had before. So we've done this part here, which is look at the slow time. Now we're going to look at the fast time, a slow equation, and see how it behaves on top of the slow manifold, and how often it falls off. So I write the slow equation. It's very easy because it's linear. Okay, but it's linear in y1 and y2, but it has this nasty habit of y1 and y2 being a nonlinear function that I have to invert, right? Because I have to get x1 and x2. Well, maybe I can do this. x1 and x2 here, I have to write as inverse of f of y1 and y2, and of course I cannot invert f, as you can see. It doesn't have an inverse. So I could write a local inverse for f in each one of the components and so on, but it's easier just to do it the other way around. You look at this expression here, pressing the wrong button, this expression here, differentiate that implicitly, substitute the derivatives, and you get the projection. Instead of studying it in the slow variables, you study it in the fast variables. So I differentiate this, get this side, and this is y dot, y1 dot, y2 dot, copied from up there. Of course, I still have to invert this matrix, but inverting matrices is easier than inverting nonlinear things. And also you can do most of the study without inverting it, just looking at this thing as it is, as an implicit differential equation. Okay? If I only look at this law, here I replaced y1 and y2 by f. If I look at it this way and just ignore this part, I have to be careful because I reverse the flow orientation in some of the non-attracting parts. Every time I cross a fold line, I'm crossing a place where this matrix is singular, and then I reverse time orientation. But that's something you can live with. Okay, that's it stopped. I was going to do an Egyptian dance or something like that. Sonic dance. This is a plot of the direction field of the slow equation for one type of variable. You can have a look. I've painted on top the fold lines, so you can see that I'm interested only in the outside of these fold lines. This is just a direction field. All the vectors have the same size. So you can see there's here an attracting node for these values of the parameters. There's another one here. But if you remember, if you're flowing around here, you go, and you reach the fold line, because all the time here in this component, the vector field is pointing outwards. So it's trying to jump off the cliff. And here again, it's trying to jump off the cliff. So it's going to jump and it's going to eventually land in one of the other components. And if it lands in this component or that component, then it goes here. It doesn't jump off the cliff. It goes to this sink, and here it goes to this sink. But that's for one particular choice of parameters, right? How does it? Sorry?
Where are the Turks here? The Canards.
The Canards. Oh, I haven't talked about Canards yet. They are going to appear. You're telling the end of the story. Come on, lad. I went to kill my ducks in due time. Okay, so I've started cleaning things out by looking at the parameter values. If the delta is 0, and if this gamma, let me see, where is gamma? Gamma is the slope of the slow equation, right? And delta is the offset of the slow equation, right? That line, when I had a single Fitzhugh-Nagumo, maybe I draw it here. I had something like that. And I had, this line has slope 1 over delta, over gamma, and delta could be here. This is delta, minus delta. Is this position of this line. That's the line y dot equals 0. So let's go back to it. So when delta is 0, so this line goes through the origin, except that I have 2 of them, right? And and gamma is small, then the only equilibrium of the slow equation is the origin. So I have this one here, but not that one on top. When gamma reaches this value, I get a saddle node and create two equilibrium at these points, which are outside the attracting part of the slow manifold. And then I get, for larger gammas, I get a saddle and a node, and the node eventually migrates, with delta equals 0, migrates to the attracting part, which is what I've shown you here, right? It migrates here, and the saddle, this part is a bit messy. I didn't worry much about it because it's very unstable. Okay? If the coupling is symmetrical, still I have a gamma 0, so each cell is being pushed with the same, each equation is being pushed with the same strength as the other one, then, oops, whoop, what is going on? You have a saddle node at a fold point for this value. So that's a complication. That's worse than a canard for Lev, who wants the end of the story. That's a complication I don't know how to deal with. That's a more degenerate point than I know how to deal with at the moment. But for larger gamma, it gives rise to a sink, which is what I want to see. Okay. And if by choosing correctly the different parameters, I get this attracting equilibrium moving into the fold line, which is reasonable. So let's see how you do that geometrically. This is the line, this blue line is the line y1 dot equals 0. This red line is the y2 dot equals 0, and they're crossing at only one point, which is the origin, right? So I have only this equilibrium. When I increase the gamma, so this is for gamma less than 1, and for these parameters, the saddle node is at gamma equals 1. I'm just slightly over gamma equals 1, 17 over 16. Then they have already undergone the saddle node. That's the saddle, that's the node, and the origin is still in equilibrium. Okay? And if for large, really large gammas, 2, not that large, then I start getting other equilibria, like here, 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 well, this one, okay, and I start getting equilibria on the other components of the other attracting components of the slow manifold. And when you have asymmetric coupling, you deform the picture, but it's basically the same thing. But you may not have any equilibria on this component, but you may have 2, for instance, here. Okay? So it's always 2 cubics through the origin if delta is 0. If delta is non-zero, I'm moving this thing here, I get more general cubics. They don't go through the origin anymore. But what the important thing is that whenever the 2 cubics cross, you have an equilibrium. And if they cross in the attracting component of the slow manifold, they're always sinks. They're always asymptotically stable, right? Okay, but for codimension 1 values of the parameter, the equilibria we are going to hit the fold line. So what's going on on the flow line? So when it is on the fold line, that's something that has been studied. So it's an application of singularities. It is something called a folded node, which I'm going to show you what it's like in a moment. So a folded node is something like that. It's your slow manifold here. Here's the line of folds. your node here. As I said, it's attracting, this point is the node, it attracts the flow. Of course, in this part of the slow manifold, I said you're inverting the direction of the flow, the time orientation. So instead of attracting, it's repelling, right? That's because of the way we're setting the problem. So here we have a folded node, and you notice that trajectory is starting here. This is gray part, here is the attracting part of the slow manifold, and the blue one is the repelling one. So trajectories, oops. Well, okay. Trajectories that start on top here, they drop off the slow manifold, they jump off the cliff. But in this region, they're all funneled into this singularity here. And here you have a conflict, because the fast equation has a zero, and the slow equation also is zero. So there's a competition. And for trajectories that are trapped here, what happens is that some trajectories get funneled into the unstable part of the slow manifold. So they start following the unstable part. Although it's unstable, they follow it for a while. And then they jump back into the attracting part. So they may jump up or down if there is a component down. And remember, in our model, we had 4 components. So there's lots of places for it to jump to. Okay? So they jump. And if they jump, these trajectories jump always into another component. But these trajectories in the funneling region may jump back to the same component, and they may do it several times. So that's what Lev wanted to talk about, the canard, a solution that comes from the attracting part of the slow manifold, gets to the edge of the cliff, and then follows like people who climb rocks. Okay, they sort of climb the roof and then jump back. Okay? And then this is going to generate, this is what's going to create what I'm looking for, which are bursts, like little wiggles like that instead of a big jump. Okay? So that's the end of the story so far. I'm going on with this. And I have a final comment about this talk. Some of you who were here 2 years ago and have a very good memory may notice that this talk is very similar to what I talked last time. Probably most people don't remember that far. But the curious thing is, 2 years ago it was all numerics. Now I have proofs. So thank you for your attention.
Thank you very much for the interesting talk and video dancing. Are there any questions?
About the canards again. There are some, let's say, classical results on the canards.
Yes.
So that you have a sort of higher dimensional situation than the usual canard, right?
No, but because I could give you a sort of
You know,
list is long of people who have studied this thing in 4 dimensions.
I didn't finish. The question is that if you take this one-dimensional canard situation and then you just deform it, then you have some canard-like bifurcations. This is what you mentioned once, that you have some more difficult behavior than the canards.
Yeah, you can also have a saddle node on the line, on a fold line.
This is the question. What is the geometry, and have you some additional information about that?
No, but I know where to look for it. But I can tell you offhand. There's a lot of now. There's a lot of results of other people that I can apply. And I know, I'm conscious of that. But I was trying to first to establish which cases, because you can have a folded saddle, a folded node, a folded focus, a folded saddle node, lots of things. And all of these things have been studied. So I wanted first to establish, in this case, exactly which ones I wanted. Now starts the really serious dynamics part. The other thing I would like to do was to do this not with this equation, but a class of equations. But as I said, I prefer to first work well an example and get a feel for what's going on. So yes, there's a lot of stuff to be done now. And there's a lot of literature on what happens in these dimensions.
For instance, that canards, they appear in exponentially small set of parameters, usually. And these higher bifurcation, they appear also in this sort of slope, where you have, they appear in some double exponential. Just what about the, let's say, quantitative theory?
Well, you have to look at it. Because, I mean, I'm just waving my hand saying the solution does this and that. You have to do a proof. But I have a proof that the geometry is this. Now I have to look at the proofs of what's the dynamical behavior and how far you can take it away from that exponentially small neighborhood. Okay? But that's, as I said, it's underway. I'm doing it slowly. I'm on the slow manifold. Maybe I should associate myself to a fast equation.
I have just one question. Do you have any physical model which is controlled by this?
The idea is to try and understand small groups of nerve cells. Okay? But there are lots of other coupled cell systems that it can be worked that way. And also it can appear as a quotient of more complicated, sort of larger coupled cell systems. And there's a lot of people doing this sort of things. You can have a really large set of cells coupled in a complicated way, but if the coupling has some symmetry, you can reduce it to just two. So it's not a sort of ridiculous thing to study two. Although even ridiculous small things sometimes are hard to understand. If I can understand two, I'm going to be happy.
Okay, let's thank the speakers again.